Till now, we have discussed the diffraction of X-rays by crystals. Now, today, you will see the problem of diffraction not by X-ray but microparticles like electrons. Why we think that electrons can be diffracted by crystals? Because after the discovery of de Broglie, it is now well established that electrons have wave character. It means the microparticles like electrons when in motion possesses wave character. A wave packet is associated with it. And you also know that diffraction is the convincing proof of wave nature. So anything which have wave character must be diffracted. So if electrons are waves, then definitely electrons will suffer diffraction. Okay? And you have definitely studied in your course of quantum mechanics a very famous experiment performed by Davison and Germer in 1927, which was actually for the diffraction of electrons by crystals. So Davison-Germer experiment already proves that electrons are waves because electrons can be diffracted by crystals. So in this lecture, our aim is not to deal with how diffraction takes place in case of electrons. But this lecture is meant for what is the basic difference between the diffraction of electrons and diffraction of X-rays by crystals. So the prime aim of this lecture is to point out those differences or to compare the diffraction of electrons by crystals and diffraction of X-rays by crystals. Okay, so the discussion would be more often a comparison between the electron diffraction and the X-ray diffraction. Okay, and for this, first of all, we will compare the energy of electron and that of X-ray photon of same wavelength. Okay, and therefore we will recall the de Broglie hypothesis. You have definitely an idea of de Broglie hypothesis, and according to de Broglie, the wavelength associated with any elementary particle in motion is given by this formula, lambda equal to h over p, where h is Planck's constant and p is the momentum of the particle. So if you are talking about an electron, then this p will represent momentum of the electron. When you say momentum, that means linear momentum. Okay. Now if we consider a free electron, when you say free electron, it means the electron which is free from force, or in other words, you can say that a free electron means an electron whose potential energy is zero. So let us consider an electron whose potential energy is equal to 0. And if potential energy will be 0, then the total energy of the electron will be simply equal to its kinetic energy. Okay. So if you denote the total energy of electron by the symbol E, that will be simply equal to its kinetic energy K. Okay. And kinetic energy is related to the momentum by this relation, that is, it is equal to p square over 2m. Okay, this is a well-known formula. And that's why you can say that momentum of the electron having energy E, that will be equal to p equal to a square root of 2me. So in this expression for wavelength of electron, you can replace this momentum p by this expression x square root of 2me. So if a free electron has total energy E or kinetic energy E, you can say, then its wavelength will be given by lambda equal to h over a square root of 2me. Okay. Now you can see this formula. In RHS, apart from this energy E, H and M are universal constants. Okay. And you know the value of H is this much. This is 6.63 times 10 to the power minus 34 joule second. And mass of electron, this is 9.1 into 10 to the power minus 31 kg. You should remember that this formula which I have written for the wavelength of electron, this is valid only in case of non-relativistic motion of the electron. It means you are considering that electron is traveling or moving with a speed v which is much smaller than c. So in a non-relativistic limit, the wavelength of the electron will be what? That will be lambda equal to h over 2m square root of 2me. Now when you will substitute the value of h and m in this equation 1 and you will simplify it, then you will get simply lambda equal to 12.27 divided by square root of E angstrom. Okay. Actually the result will be this much into 10 to the power minus 10 meter, and as 10 to the power minus 10 meter is 1 angstrom, so lambda will be this much after simplification. Actually roughly we also write that lambda is equal to 12 over root over E angstrom. 0.27 is neglected. Okay. We also write like this. So this is the wavelength associated with an electron having energy E. Okay. Now you know in a diffraction experiment of X-ray, normally we use the X-ray of wavelength of the order 1 angstrom. So let us think about if the wavelength of electron is also of the order of 1 angstrom, then what will be its energy? It is very easy to calculate this value of energy from this equation 1. So you can see if lambda is equal to 1, then according to equation 2, 1 will be equal to 12. I am not writing 12.27 but 12 over a root over E. Okay. And so E will be simply equal to 144 electron volt. You must remember that in equation 2, this energy E is in electron volt. Okay. This is in electron volt. So what we get? You can see that the energy of an electron having an wavelength 1 angstrom will be almost equal to 144 electron volt. Okay. I think it is very clear to you. This is a simple calculation and you can easily understand it. Okay. Now we will see what will be the energy of X-ray photon having the same wavelength. It means if we consider that there is X-ray whose wavelength is 1 angstrom, then what will be its energy? Let us now calculate. As you know, for X-ray photon, energy E is equal to h nu, where nu is frequency of the radiation or X-ray, and nu is equal to c over lambda. Okay. Now this product Hc, this is actually 12.4 into 10 to the power 3. Okay. When you will substitute the numerical value, you will get this. So lambda, which is equal to Hc over E, that will be equal to 12.4 into 10 to the power 3 divided by E angstrom, where E is in electron volt. Okay. And so if you will put the value of energy E in kilo electron volt, then this 10 to the power 3 will cancel out and your result will be like this. lambda equal to 12.4 divided by E angstrom, where E will be in kilo electron volt. Okay. Now you can see that from this relation E will be equal to 12.4 divided by lambda. Okay. So if we will take lambda equal to 1 angstrom, okay, then what will be the energy? You can see energy will be equal to 12.4 kilo electron volt. Mark this, kilo electron volt. Or you can say 12,400 electron volt. This is 12,400 electron volt. So what we are getting here, you can compare that for electrons of wavelength lambda equal to 1 angstrom, energy is equal to 144 electron volt. But for the same wavelength of X-ray, that is X-ray of wavelength 1 angstrom, energy is equal to 12,400 electron volt. So you can see the energy of X-ray of same wavelength is much greater than the energy of electron. So it is obvious when electron will strike a crystal, it will penetrate little less than that of X-ray. So penetration ability of X-ray will be much more than that of electron of same energy. This is a fundamental or basic difference between the electron's energy and the X-ray energy of the same wavelength. And that's why the diffraction of electrons by crystal and diffraction of X-rays by crystal differ much more. They are not just identical. Although there will be some similarity, but there are so many dissimilarities in diffraction of electron by crystal and X-rays by crystal. And as I have told you earlier, the aim of this lecture is only to differentiate, only to compare these the diffraction of electron and the diffraction of X-ray by crystal. Actually, this concept is very useful for the students preparing for the examinations like civil services examination, taking physics as an optional subject. You can see the previous year question of civil services physics optional, and you will find several times this question has been asked. Okay. So I have prepared this lecture meant for those students particularly preparing for the civil services examination, taking physics as an optional subject. Okay. Now the second basic difference between the diffraction of electron and the diffraction of X-ray by crystals, we will now let us see. We will now see. Actually, you know, when X-rays are incident on a crystal, then diffraction of X-ray is due to the electrons, only by electrons of the crystal. But in case of electrons, when a beam of electron is incident on a crystal lattice, then it is scattered not only by the atomic nucleus but also by atomic electrons. Okay. So you can say that beam of electron is scattered both by atomic nuclei and atomic electrons. Okay. And that's why the electrons get much more diffracted than X-rays of same wavelength. Okay. And this is the reason that electron diffraction is much more intense. It means intensity of the diffracted beam of electron is much more greater than the intensity of X-ray diffraction. Okay. Actually, this idea was described in very detail by famous scientist Mott, but I am not providing here you the complete theory of Mott. We will directly write the expression for the scattering factor of for electron and how the scattering factor of electron is related to the scattering factor of X-ray, and then you will compare it. Actually, Mott has found that for a spherical charge distribution, the scattering factor Fe, when you say scattering factor, that also means a scattering cross section. This is denoted by the symbol Fe. This is a scattering factor for electron. And this is given by this is Mott's formula, and you should remember it. Okay. This is given by me square over 2h square times z minus fx times lambda square by sine square theta. You have to remember this formula. Actually, in this expression, this fx denotes the scattering factor for X-rays. Fe is a scattering factor for electron, and fx is a scattering factor for X-rays. And Z is actually nuclear charge, or you can say that this is atomic number, or you can say this is number of protons in the nucleus. Okay, this is atomic number. Okay, but I have written nuclear charge because when you will multiply it by the charge of a proton, then you will get the nuclear charge. And theta is Bragg angle. It means this is glancing angle, you can say. Okay, angle of glance or glancing angle. Now see this equation. As you know, when theta increases, then sine theta also increases, because theta lies between 0 and 90 degree, and in this limit, with increase in theta, sine theta increases, because sine 0 is 0 and sine 90 is maximum, that is 1. And if theta will increase, sine theta will increase, and as sine square theta is denominator, so the value of Fe will decrease. So I have written it here, you can see. It is clear that a scattering factor for electrons, that is Fe, decreases with increasing the value of theta. Okay, and actually the same phenomenon takes place in case of X-rays. So in this context, you can say that the variation of a scattering factor with theta for electron and that for X-rays are similar to one another. So I have written that the same behavior as X-rays. It means X-ray, in case of X-ray diffraction, it is also seen that with increase in theta, the scattering factor decreases. Okay, but the scattering efficiency of atoms is considerably greater for electrons than for X-rays. Okay, now we will see the another very important difference between the diffraction of electron by crystals and that of X-rays. Actually, you know, electron is a charged particle, it possesses negative charge. So when it strikes the crystal, then this electron suffers, or this electron you can say experience repulsion from the atomic electrons of the crystal. And due to this repulsion, the electron cannot penetrate much more in the crystal. And that's why you say that the penetration ability of this electron is much more less than that of the crystal. And that's why This electron diffraction may take place from a thin film. If there is a thin film, then and you incident the X-ray beam on it, that cannot be diffracted. A thin film cannot act like a diffraction aperture for X-rays because the penetration ability of X-ray is very high, and that will penetrate into the thin film, and not they will actually scattered or diffracted. But since the penetration ability of electron is very low, why penetration ability is small? Because the electron will experience repulsion from the atomic electrons of the film, and so that it will not penetrate much into the target, and so from a thin film electrons get scattered or it gets diffracted, but X-rays are not. So for the study of thin film, electrons are the most appropriate candidate for diffraction. Okay, so I have written it here that these electrons easily diffracted by thin films or thin layers. Okay, and therefore electron diffraction is very useful in the study of a structure of thin films or thin layers, such as oxide layers on metals. Okay, like when you say zinc oxide and you have to study the oxide layers structure, we will use the electron for diffraction, not X-rays. Okay, I think this point is very clear to you. Okay. Now, such layers are not detected by X-ray, as I have told you earlier, because X-ray penetrate deep into the solids and produce patterns that are characteristic of interior of the material. Okay, so X-ray cannot be used for the study of a structure of thin films, because when these X-rays will incident on the thin film, that will penetrate into the film, and it cannot be diffracted, and so X-rays are not used for the study of a structure of thin film or oxide layers on metals, but for this purpose electrons are used. Okay, I think you have clearly understand. Okay. Now I have marked here two very important problems which are actually studied, or which are for the study of which we use the diffraction of electron. Okay, first one is a study of orientation, lattice parameter, and perfection of evaporated thin films. For these purposes, we use electrons as the candidate for diffraction. Okay. The another problem is the regularity of the atomic arrangement in a thin film varies over regions of crystal imperfection. Okay, and the electron diffraction studies made in the electron microscope reveals these imperfection. So if there is imperfection in thin film, and you have to study that imperfection, then you must use the electron beam, energetic electron beam incident on the thin film, and the diffraction pattern will actually give you information regarding that imperfection. Actually, this technique this is actually done by the use of electron microscope. Okay, so these are the important basic differences between the electron diffraction by crystal and the X-ray diffraction. And as I have told you earlier, our aim in this lecture is not to discuss the experiment for the electron diffraction, but only to compare what is the similarities and dissimilarities in electron diffraction by crystals and X-ray diffraction by crystals. And this type of question is very invariably asked in the examinations like civil services. Okay, thank you very much.